All right, ladies and gentlemen, class recording has started. So, today, we are going to continue on with the example problem that we started yesterday. This example problem shows up on page 159 of your book. Right in the middle of the page, there's a big section that says example problem. There it is. So it says, the ball in the strobe photo was launched with an initial velocity of 4.47 meters per second at an angle of 66 degrees above the horizontal. And then there are three parts to this problem. First, what was the maximum height the ball attained? Second, how long did it take the ball to return to its launching height? And third, what was the range? So, yesterday, we started in on part A. And we said that there is nothing different about how we start this problem. So we still go ahead, make ourselves a chart. Horizontal side, vertical side. And we said that there's still the five things that we're looking to analyze. VI, VF, acceleration, displacement, and then time. And we said that the first thing you can fill in on this chart does not change. We still have 0 acceleration horizontally, and we still have 9.81 acceleration vertically. Because if we neglect air resistance, there's nothing acting on it horizontally, but gravity affects it vertically. Okay? Good there? All right. To solve for this problem where it says, what is the maximum height? What's our unknown in this problem here? What are we trying to solve for? Displacement, especially, Ben, which way? Vertical displacement. That's what we're looking for here. We want to know how high this ball ends up. Maximum height. Okay? So we filled in our chart, we got our unknown. The thing that changed about yesterday's problem was that now it says that this object was launched with an initial velocity of 4.47 meters per second. But it was not launched horizontally. Right? That it says that it was launched at an angle of 66 degrees above the horizontal. So, at this point, right here, that spot when it first gets launched into the air, it was doing this. Right? That sound familiar from yesterday, those of us that were here? And we said that this is 4.47 meters per second, and that it told us that it was launched at an angle of 66 degrees. But if this object is moving at an angle, what does that mean that it's doing? It's traveling horizontally, but it's also traveling vertically. That this combination of 4.47 meters per second at 66 degrees is actually a combination of this motion and this motion. Right? That it's actually going both sideways and up at the same time. The result of that is 4.47 meters per second at 66 degrees. Good with that? That's how this problem changes. So, we made use of some math stuff to help us out. This vertical part here, we slid over this way. And we made ourselves a triangle. But because the blue is horizontal and the red is vertical, we know that this has to be a right angle. And if that's a right angle, we have a right triangle. And if we have a right triangle, we can use some trig to help us figure out the other sides. Okay? So, the red side, based on the angle that we were given in this problem, the red side is the opposite side. We know which side of the triangle? The hypotenuse. So the relationship between opposite and hypotenuse is given to us by which trig identity? Sine. So we used sine, and we figured out that this side of the triangle was what? 4.08? Is that what it was? Yeah? If I remember correctly. Okay. So that was that side of the triangle. Then the blue side, based on the triangle that we know, the angle that was given to us, is the adjacent side. We still know the hypotenuse, so we can use cosine then to find the blue side of the triangle, and that was 1.82. Okay. So this would be 1.82 meters per second. Okay. Now, why is that important? Because at that moment, at the very launch point, remember, this triangle only applies right at the spot when we launched it. Okay? Does it ever really travel along this purple arrow that we've drawn out here to represent the initial velocity? As soon as we launch it, what starts happening to it? It starts going down because of gravity, right? So this purple arrow could represent where we intended to launch it, right? But it'll never follow that path. Gravity starts pulling it off of that path immediately. But at the very beginning, at the launch point, this is what's going on. So we said, what can we do now with those two numbers? Did we get there yesterday? Okay. These two sides of the triangle become the initial velocities both horizontally and vertically. We refer to these two sides of the triangle as component vectors, which I think I neglected to tell you guys yesterday. These two sides of the triangle are the component vectors of the initial velocity. As far as our problem is concerned, that means that gives us the initial velocity horizontally and vertical. All right, good so far? Okay, I think that's where we left off yesterday. Is that correct? All right, one more thing we can fill in as far as our chart is concerned. One thing that still holds true from the horizontal problems. One other thing. I go. The final velocity horizontally has to be 1.82 because we have zero acceleration. Okay? All right. Do we have enough information to solve for what we need to solve for?
Isn't the final velocity zero?
Okay, so I couldn't remember if we got that far or not.
Yeah.
Right? All right. In this picture, right? In this picture showing the strobe photograph of this flight of this ball, right? This problem is really only asking us to analyze that part of the flight because its maximum height occurs right here. Okay? And I think we talked yesterday that going back to our one-dimensional motion, if we take this ball and throw it straight up into the air, what do we know happens up at the top? Stops, right? Just for a moment, just for an instant, but it stops. We talked about that the projectile motion idea states that if we have a horizontal motion now occurring with our vertical motion, does anything about the vertical motion change? Horizontal and vertical do not affect one another. Vertically, if I take it and toss it now at an angle, ready? At its highest point, is it at rest? No, because it's still moving how then? It's still moving horizontally. But at the highest point, right here, vertically, what can we say is going on? What would be its vertical velocity?
Zero.
It's zero. So for this part of this problem, the final height is going to be zero. That only applies at one point and one point only. What is that one point? At the very top of the motion. So for this specific problem, when it's asking us to find the maximum height, we can assume that VF is equal to 0. That doesn't apply for every problem. Just here, when we're trying to solve the maximum height. Okay? Did I make that point clear enough? I want to make sure that whenever we see this picture right here, people don't just throw in VF equals 0. Okay? Only if we're finding maximum height. Now, do we have enough information to find what we're trying to look for in this chart?
Yes.
We do. Do we even have to solve for the time at this point? We don't even have to solve for the time, right? Here, right, we have three pieces of information on the vertical side. We pick the right kinematic equation. We can solve for what delta y is. So go ahead and do that now if you haven't done so already. care of this, but I forgot to make a point here. Okay. I purposely left it out, and then I forgot to do what I was supposed to do. So, we got our vertical stuff, right? But it's important now that in the vertical dimension, we take care of sines, yes? Because this initial velocity that we calculated, the 4.08, that shows up right here, which direction is that going? Up, right? But which way is gravity pulling on it? Down. So we have to make sure that we distinguish that in the vertical dimension. Because even though there's two things going on at the same time, remember they're independent of one another. That means that there's an up and down vertically, and then there's different directions horizontally. But right now, everything's in the same direction horizontally. But vertically, we got to make sure we take care of that. Sorry about that. I was going to tell you guys about that, and I forgot to.
Wait, but then you'd have a negative distance.
No, not if you do it right. What? Dave, did you get which equation did you use?
I saw for time, whatever.
It's actually 0.849.
But that's a height.
Yes. That's how high we threw it into the air.
Oh, so we didn't throw it a meter
No,
in the air?
because 4.47 meters per second is pretty slow.
Oh, so that's just.
Yeah. All right. So when you solve for this, did we get a delta y of equal of 0.849 meters? Did you take the square root? No way. Make sure you square your stuff. Oh, 0.848. Okay, sorry. The book has 0.849. So. All right. Go ahead, Mike.
When I did, I got 0.846. So
You might have, Kamani, you might have just, hey, listen. Kamani, you might have just used like some different rounding as far as the initial velocities were concerned.
as
Like,
long as we're like in the
yeah, if you're in the ballpark, that would. If you wrote 0.846 and that was your answer, I would be fine with that. So. At first, because I would look at it, I would see that it was different than like what I had, but I'd probably then go back up and look at your beginning numbers and say, oh, she used some different velocities. That's all. All right, are we good there? You didn't get that? Let's work on that. Yeah. Let's do it. Go on to the next one. All right, so now moving forward, there is a second part to this problem. So I'm going to grab this problem here.
What are you gonna use it for? Flowers?
All right. Part B. Part B of this problem says, so part B of this problem says, how long did it take the ball to return to the launching height? So, whereas A basically wanted us to stop here, B now wants to take it all the way back over to here. Okay? The way you do this problem is no different than the way, or at least starting, is no different than you do the other problem. So we set ourselves up our two lists again. Okay? Horizontal first, vertical second, VI, VF, A, delta XY, and delta T. Again, we can plug in the acceleration right away. 0 horizontal acceleration, 9.81 vertical acceleration, but we've already sort of established the fact, so we don't get in trouble, that that has to be negative. That's the beginning. This problem asks us for how long, right? So what is this question asking us to solve for? Time, right? It's asking us to solve for a time. What did we learn about time at the beginning of this unit? Okay. Does it matter whether we solve time horizontal or time vertical? It does not. Either one of them will get us the time. So we can put question marks in both of them. All right, now, So let's keep going. Let's go back. Okay. We said that.
That's the funny thing.
That was Tyler, the answer to your question is yes.
He's like,
This triangle that we found the component vectors of the initial velocity, we said that applies at the launching spot when it becomes a projectile. So, in this problem, even though now we're trying to find out a time that relates to the entire flight, was there anything different about it at the beginning than there was at the beginning of the last problem? No. So this is still 1.82. This is still 4.08. And now we can still keep this as 1.82 as well. Good so far? Okay. Now, I tried to stress in the last problem that we can only make the final vertical equal to 0 at one point. And what is that one point? The maximum height. This is the only time that the vertical velocity is 0. But we're looking at another part of this problem, way over here on the end. The important part here is that it returned to launching height. That's the equivalent, right? That's the equivalent of, if I throw this ball straight up in the air, where do I catch it? Exactly the same spot I threw it from. What did we say about the speed of the ball when I catch it versus when I throw it? It's the same speed, but different direction. So we can actually fill in for this spot over here, the end of this flight, if it lands on the same level, we can make two assumptions. First, what is the final vertical velocity of that ball going to be? Negative 4.08. The displacement of this ball vertically bent is going to be 0. Because on the vertical side, it has gone up, right? And it's come straight back down right to the spot where it started. So vertically, its displacement is 0. Does that make sense? These two things that I just filled in, this one here and this one here, the final velocity being negative 4.08 and the vertical displacement being 0, only apply at one point only. And what is that point? When it gets back to where? Where I threw it from, or where it started from. Those two things only apply at that point specifically. Okay? Now, do we have enough information to solve for time? Yeah, there's a couple of ways you can do it. Okay?
I mean, you really didn't even have to figure that out, did you? Because you already finished.
No, we didn't do, like, Tyler, to fill in this and to fill in this, we didn't do any calculations. That's just our knowledge of projectile motion helping us get more things, because we really want to solve for time, right? So, go ahead, solve for time.
For time? But I'll do it.
This strobe picture isn't the best. Right?
You don't like the strobe picture?
It's like, wait, it looks, the arc's too much. It's like a very shallow throw.
It is, well, it's actually like,
It's actually only this far.
if you,
I know.
it's like this throw, right? Are you ready? It's like this. Right?
No, I'm ready.
It's like,
No, not even.
I mean, it didn't even go up a meter. You know what I'm
I know.
saying? So,
That's why this is very misleading.
It is very misleading.
Did you get crazy?
Yeah, 0.832.
ooh.
Like, it wasn't even in the air for a second. Yeah, it was like that. It was just like that. Pixel. Who's that paying attention?
Alright, so did we get 0.833 as far as our time? Rounding.
No, I rounded it.
Well, you guys might have been using a different initial velocity, like the components, you know?
I used all those numbers on there.
What if you use the first equation?
So, good question, alright? So, Tyler asked, you have three things over here on the other side, right? Could you use that to solve for time? But when you do that, we run into the problem of you get like 1.82 equals 1.82. You remember that from last week? Or you hear from last week? I can't remember you here for that. You don't get 0 when you solve that. You actually get a number, but it doesn't give you what you want to know. Alright, last question. Last part here says, part C says, what was its range? Range is a new vocabulary word. Okay? Range is, where do I have to stand to make this thing land on my head? Right? So that means that if it's asking for range, it's really asking you to solve for what? It's asking you to solve for horizontal displacement. The range is the horizontal displacement. So, do we have to do any new calculations to help us solve for delta x? No. We've already established that if you know the time vertically,
I'm trying to record here. I'll hear the conversation. Make it hard to record.
if you know the range, or if you know the time vertically, you also know the time horizontally. And now we've got information that we need over here on the horizontal side, so we can solve for what the range is going to be.
The story for me. Miss less of this period than I thought. Favorite cars. No, you can't get cars. Dude, how much is it?
Alright, so we get 1.51 meters? Alright. Next example that I want to do with you, very similar. I'm going to go to page 172. And does anybody have a real strong feeling about a problem related to archery or related to baseball?
Let's use this. Let's use this. Let's use this.
To archery. A slingshot that launches things 300 yards. Possibly.
Not quite that far, no.
Only $50.
Actually, okay.
Dude,
How far
we
could
could
change it into a slingshot?
No.
Alright,
Dude, you could kill someone.
How about a
this
sling-
problem,
You can make like a little. You should make a little cover to the top, and we're gonna get like a missile.
so,
So, we could sit at the, because lunch stuff and just like such a fire and stuff.
A was the point 848.
Ben's World.
Whoa.
No, he asked a question.
Yeah, Sean was asking a question.
Yeah, we were doing
So-
physics problems.
This problem shows up on page 172. It's problem number 42. So it says an arrow is shot 30 degrees above the horizontal. Its velocity is 49 meters per second and it hits the target. So two questions. What is the maximum height the arrow will attain? And B, the target is at the height from which the arrow was shot. How far away is it? So starting off, for part A, we set ourselves up our chart. Nope, not that.
Easy. Okay, we're recording.
There's gonna be a lot of that.
So you
during this
probably
recording.
bleep it out. Probably shouldn't swear while everyone else is quiet.
Well done.
Okay, so we start off. Hey, we're still trying to record, regardless of whether you're swearing or not. So, set up our chart, right? We can fill in two things right away. Horizontal acceleration, vertical acceleration. Part A, what is the question asking us for? Maximum height. And we said that maximum height's going to be what variable in this chart?
Delta X, Y.
And it's going to be the vertical displacement. So, picture, right? There's like that, right? So it says that this arrow is shot like this, yes? And it tells us that it has a velocity of 49 meters per second, and it's shot at an angle of 30 degrees. Okay? So we can use that information to find what? Not VF. We can use that information to find this and this. From a definition standpoint, what did we call those two things?
The opposite.
The component vectors. So we can use the facts that the arrow was shot 49 meters per second, 30 degrees above the horizontal, to find the component vectors. We said the component vectors become what in this chart over here?
Initial.
Come our initial velocities. So go ahead and figure out what the component vectors of this velocity are.
Yeah, the opposite. Can do that one.
Yeah, I'm already done. It's 30 minutes.
Figure the radians.
How are you guys just doing? You could do serious damage to somebody.
Dude, you could hurt
that-
somebody.
From that far away. What do we do here? Add power? Let's do it.
Alright, so finding the component vectors. Finding the component vectors, we see that the initial vertical velocity is 24.5, the initial horizontal velocity is 42.4. This is in the upward direction, so that's positive. The acceleration being from gravity pulling it downward is in the negative direction.
Yeah, it's 0.
In this case, because we're looking for maximum height, we can say that the final vertical velocity is equal to 0. Once we do that, now we've got three things over on the vertical side. We can solve for delta y.
It's on your end there. Somebody.
It's pretty high to shoot, right? You hit your target that far.
Especially because you did 30 degrees, really isn't that? All right. We're good with 31 meters? So,
Pick up.
we do this. All right. For part B, it says the target was at the height it was shot from. How far away is it? If it's asking us for how far away it is, what is that asking us for? Horizontal displacement. Okay? But a couple of things change. First, right? Obviously, obviously, if it hits where it went from, the vertical displacement isn't going to be 31 anymore. Also, the final vertical velocity isn't going to be 0. Now we're dealing with, right, all the way over here where that object hit its target. But because it says that it was shot at the height, we can make two assumptions on the vertical side. First, vertical displacement is 0. Second, final velocity, negative 24.5. That only applies, though, if the target is at the height from which it was shot. Now, we can solve for time vertically. You can use that time horizontally to solve for horizontal displacement. Okay? When you do, you should get 210 meters. So, two things. For tonight, it was actually homework from last night, but we didn't get very far on it. On page 160 of your book, there is a section called Practice Problems. Number 12 and number 13 are very similar to the problems that we did in class. Because it's in a practice problems section of your book, the answers are in the back of the book. So you can check out what the answers are. So homework tonight, page 160, number 12 and 13. We'll change it up tomorrow.